let's take a closer look at problem 2. So the following sets are written using set abstraction notation. Please list their elements explicitly. So we will exhaustively enumerate those elements that are in this set. So the first set says x is an integer and x mod 2 is equal to 0, which is the same as saying the number is even. X divided by 2 has a remainder of 0, so it's an even number. And the absolute value of x is less than 8. So with that, if the absolute value of x is less than 8, then x is less than 8 or greater than negative 8. So I know it's in there, I know it's an integer, and I know that it's even. But it's strictly less than. And so I know that this is the set -6, -4, -2, 0, 2, 4, and 6. And I don't include the 8 because it's strictly less than 8. And so that's my list for the first piece. All right. So part B says x is prime and x is composite. Here's a problem. Numbers are not both prime and composite. And so this answer is easy. If I write it out, I can write it as the empty set, or I can just have a set with nothing in it. They're the same. Either works. Okay, so for part C, we have x is an integer, and x is equal to 3 to the y for some y in the set of integers that are greater than or equal to 0, but less than 6. And so first we have to figure out what that set is. So we know that y is in the set, k is less than 6, and it's an integer greater than or equal to 0. So 0 is in that set, less than 6. 1 is in that set. 2 is in that set. 3, 4, and 5 are all in that set. And that's it. So using what we know about y, then we know that this set is the set of integers, x equals 3 to the y, where y is in the set 0, 1, 2, 3, 4, and 5. So this is a set 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4th, and 3 to the 5th power. And we can figure out what those are equal to by just doing a bit of multiplication. We have 1, 3, 9, so that's 1, 3, 9, 27, 3 to the 4th is 81, 81 times 3 is 243, and that's it. Yeah, that's it. And so that is our exhaustive enumeration of this set. Part D are all integers that are prime and for which 2 divides x. So 2 divides x. X is the same as saying x mod 2 is equal to 0. Okay, well which is the same as saying that x is even. So basically what part 2D is saying is that it's a prime number that's even. This is a very small set because we know the only even prime number is 2. After that, everything is odd. And we know no other even number is prime because 2 would divide it, in which case it couldn't possibly exist. All right, so here we have a new starting point. We are starting from x is a rational number and 2x is an integer, and so that's where we're sort of saved in this. 2x is an integer, and x is in -2 to 1. So what that means is on our number line, we've got -2 here, -1, 0, and 1. 1 is not included. 2 is. It has to exist within this space. So somewhere between not including +1, but including -2. Okay, so somewhere in there. So because x is in the rationals, it's something of the form a over b, where a and b are both integers. But we need 2x to be an integer. So 2a over b is an integer. And what that means is we either have b was equal to 1 or b is equal to 2. Otherwise, you can check with yourself that you can't have an integer in this state. So if b is equal to 3, assuming that a over b started off as a reduced fraction, we can only have the denominator of this fraction as 1 or 2 for this to hold. And so what that means is we want all the fractions, we want everything that's either an integer or a fraction over 2. So I'm going to have -2 in that set, minus 3/2 in that set, -1, -1/2, 0, +1/2, and that's it. I don't get 1 because of the fact that this said we don't include 1. We do include the -2, but we don't include 1.